Number 7 has a cart with 6 GTAs, total weight given here. That's this cart and the GTAs all together. Speeding down a 10% decline, so they're going down a hill, and they're going at 88 feet per second. Remember, that's about 60 miles an hour. 50-pound braking force is applied. Determine their speed after the brakes have been applied for 5 seconds. Okay, so we're given a hint, constant acceleration. We're going to draw a free body diagram, kinetic diagram. Let's go ahead and get started here. Let's see, so we'll take our cart and exaggerate the hill a little bit. We'll still have a total weight going down. Gonna have some sort of braking force. And we'll have a normal force. Okay, I believe that's it. And we do have an acceleration, most likely. Alright, reading back through the problem, let's see. We're going to assume that it's slowing down. So we'll draw our mass times acceleration that way and see how that works out. We have no acceleration perpendicular to the incline. We're going to use a coordinate system parallel and perpendicular to the incline, as we usually do for these types of problems. Okay, let's see. We're also given information about the decline, so let's work with that first. A 10% decline means it's 10 over 100, so theta is inverse tangent 10 over 100. So that comes out to be, let's see, inverse tangent 5.71 degrees. And just makes that number a little bit easier to work with. They start off 88 feet per second, and then after 5 seconds we want to find their speed. How are we going to do that? So rereading the question shows me that that's a known value here. Alright, so that's equal to 1,300 pounds. That's equal to 50 pounds. That helps out a lot, because now we can look at this x direction along the incline. We know this force, we know this component of the force, we know the mass, so we can determine acceleration. Once we have an acceleration, an initial velocity, and a time, we can find the final velocity. So there's our plan. Alright, so looking at the x direction, we are going to have, we've taken positive as down the hill, so we're going to have minus 50. Okay, be careful with our components. We've done this lots of times now. There's going to be a component of the weight going down and perpendicular to the incline, and a component of the weight going down the incline, and this is our theta. Alright, so in the x direction, this component is positive, and it's the sine of the angle times the weight. Alright, so it's a positive 1,300 sine 5.71. Braking force going negative x, the weight component going positive x. Those are our only two forces parallel to the incline, and that's going to be equal to mass, 1,300 pounds, divided by 30.2 feet per second squared, times acceleration in x. Okay, this one's pounds as well. So that's going to give us acceleration, pounds on the top, and all these terms. So we multiply things out, our acceleration will be in feet per second squared. So a sub x will work out to be Let's see, 1300 times sine 5.71 is equal to 129 minus 50. Oops, let's try that again. Oh, let's see, be careful with recalling. Let's just start over again. Second recall, second recall. So there's that number minus 50. So there's our net force times 32.2 divided by 1300. Okay, so acceleration 1.965 feet per second squared. Okay, hopefully if you're following along, you're perhaps have spotted a slight mistake I've made. Have to be really careful when we work with these equations on the signs of everything, whether they're plus or minus. So I've taken positive x's down. I've been consistent over here. This weight component was positive, the braking force was negative, but I drew my mass times acceleration in the negative x direction. So I have to put a negative sign over here to account for that. Okay, by working it the way I did with a positive sign right there, that would actually mean I assumed my acceleration in the positive direction. Okay, and that would give me a negative number right here, which would tell me that I assumed, working it with a positive number right there means I assumed in the positive direction. Getting this positive answer meant my assumption was correct. Okay, so the signs are a little bit difficult, but you just really need to be careful with them. It's a minor mistake, but this actually, doing it this way, is going to give me a negative number, okay, when I solve through that. And this tells me that I assumed in the wrong direction. Okay, so this negative number in my answer means I assume direction incorrectly. Doesn't mean it's in the negative direction. It means I assumed direction incorrectly. So since I assumed in a negative, the acceleration is actually going to be down. What's happening is this braking force is not enough to actually slow it down. I mean, slow it down to, it's not even enough to offset this weight component. Okay, so we're not speeding up as fast as if we had no braking, but we don't have enough braking to be actually slowing down. A little bit of a confusing situation here, but this means therefore the acceleration in x is really 1.6965 feet per second squared down the hill. Okay. So then I have to factor that into my final velocity, initial velocity plus acceleration times time. Okay, so that's 88 feet per second. So that's going to be a positive 1.965 times 5 seconds. So I've actually sped up about 10, oops, that's not squared, about 10 feet per second. And that number is 88 plus 1.965 times 5, 97.8. The TAs are having a lot of fun. They're actually Still speeding down the hill at about 70 miles an hour now.